We'll get started. I think we left off on Friday of last week, and I introduced very briefly this concept of gradient descent. Okay, so gradient descent, and we said this can be used to minimize a function. Okay, and the idea behind this is that the gradient, all right, let me have you guys settle down, please. The gradient of a function, delta f, points in the direction of steepest descent. Okay, so negative delta f will point in the direction of steepest descent. Okay, at some point, an infinitely small point, that's what the gradient does. Okay, and you know, if we visualize a gradient, if we picture a gradient in two-dimensional space, then the gradient is perpendicular to a vector that is tangent to the contours of the function, okay? Okay, so, you know, if we plotted a function in three-dimensional space, and let's say you have some kind of function that, you know, maybe it's a, just imagine this is to be some kind of bowl. Perhaps it's hard to see with my beautiful artwork. So if we have, you know, this is x1, and this is x2, and this is our f of x1 and x2. Okay, we can also plot it this way: x1, x2, and perhaps you know, we have some kind of contours like this. Then whatever, imagine we have a vector that is tangent to the contour. I don't know how to draw such a thing. Okay, so this vector is tangent. Then the gradient is perpendicular to that. Okay, this is the gradient, delta ff. Okay, and the negative gradient would then point in the direction opposite. Okay. So at this point, the direction of steepest descent is in this direction. Okay, so this is, at this point, this is the direction of steepest descent. Okay, and so the idea behind gradient descent is you take a small step in that direction, and then, you know, you take it takes you to a new point, and then you calculate the gradient there, and you take a step in this direction, and then it takes you to another thing, and eventually you keep following these small steps, and it points you to the minimum of the function. Okay, so keep taking small steps in the negative direction, and that will lead you to a local minimum. Okay. And in our case, when we're dealing with linear regression and we're trying to minimize the average squared residual, that function is what we call convex. Okay, it's convex. It's basically a quadratic function, and so the local minimum is the global minimum. Okay, so for convex functions, can I flip the page here? So and as far as for linear regression, we have a convex function, which is the average or sum, the sum of squared residuals, or the average squared residual. Okay, so let's just kind of take a look at what gradient descent could look like for linear regression here. Okay, so let's do okay, so I'm going to go ahead and close the poll here. Gradient descent for linear regression. Okay, so we said that the idea behind so gradient descent in general is the idea that the next point, xn plus 1, is going to be our, and if this is multidimensional, it's going to be our current location, x of n, and then we're going to subtract off lambda times delta f of x of n. Okay, so for linear regression, we're trying to minimize the loss function, right? Now let me just pause and say, in real life we would probably never run gradient descent for linear regression because we've already solved linear regression, right? Analytically, we know the solution to linear regression already, okay? Gradient descent is generally useful for things where that analytic solution is not possible, okay? However, I think we're familiar enough with linear regression to understand what we're trying to do, and I think this is a good example of how gradient descent works, and then we can apply it for something more complicated. Okay? So anyway, for linear regression, we wish to minimize the loss function. So what is our loss function again? Our loss function, we're going to say, is 1 over n. In vector form, it's t hat minus xw, x times w transpose, times t, vector t minus xw, right? Because we're saying w0 plus w1 x, okay? Is each of our points. So this is our loss function. We're trying to minimize this. This is in vector notation. So our loss function, if I multiply this out, will give me 1 over n times t transpose t. So effectively t squared, but it's in vector notation. So we got to do t transpose t minus 2 w x transpose t. Sorry, this is w transpose. W transpose x transpose t plus w transpose x w. So w transpose x w. Okay, so I think we've already kind of shown this earlier. And so now we want to take the gradient of L. Okay, and so we're going to take the gradient of L with respect to W. Okay, so this is the gradient of L. Okay, and so perhaps you need to look up how these things go, but what's the gradient with respect to W going to be here? T transpose T. 0, right? Because this is not a function of W, so that goes away. That's going to be 0. Okay. What about negative 2 W transpose X transpose T? So yeah, this would be negative 2 X transpose T. Okay. And then over here, I've got W transpose X W. So with respect to W, so we can almost treat this as if it were W squared, so this becomes a 2 times X transpose X W, right? Okay, so I can just factor out a 2 or a negative 2, however we want to do this. I can do negative 2 over n, and we will get X transpose T plus X transpose X W. This is my gradient. Or if I just factor out a positive 2, then they switch around, and we would get X transpose X W minus X transpose T. So however we want to do this, okay? But we can probably just take a look at this. All right, so we'll say, here's our gradient. This here. This is the gradient, gradient of our loss function with respect to W. Okay, and then so using that, we're going to try to find the set of W's that minimize our loss function. Okay, so we're going to say the next set of W's that we use will be our current set of W's, and we're going to subtract off some lambda times our gradient at our current point of W. All right? Yes, question?
Does it matter whether or not the W transpose out or W?
What? I'm sorry, maybe I don't understand your question.
Because in the last term, the W transpose X W, does it matter which W
I don't think so. Let me think. Because effectively we're just making this a scalar. So x transpose x is going to give me a, yeah, so whether you put the w up here, w transpose up here, or the w at the end, the way w transpose x is a scalar, x transpose x w is also a scalar, so we're okay there. Yeah.
Shouldn't that be minus x transpose x?
Where? Oh yeah, right here is in minus. You're absolutely right. You're absolutely right. Thank you. Yes, sorry. I apologize. This is a minus there. Okay, so here we have this, and we can program this in R, okay? So we're gonna implement gradient descent in R using this as our guideline, okay? I've posted the code for that on CCLE, this is Stats 10, under vectorized, I think. There's two versions of the gradient descent. One is using partials, and I'll show you that. And then there's also gradient descent vectorized. So that code should be there, okay? And so here's our vectorized thing. Oops, I guess, oh, something happened. Which one of these is the one I want? Okay, so we want the vectorized one. Open, please. Shoot. Okay. Okay, so here we go. Let me just kind of quickly run through this code here. So here is my x vector and my t vector. These are basically x and y points. Something happened? I don't think so. Let me just delete all of this. Okay, and I'm going to create my x matrix here. So x matrix looks like this. This is my, my x vector and my t vector. Okay, and so this is what we have. We can solve for our thing doing what? X transpose x inverse x transpose t, right? And this already gives us, we already know the answers that will give us the minimum of the intercept and slope that will minimize the thing for us, okay? So here, I'm just going to start off and I'll just say, here's a w vector we can start with, okay? We're going to just say we'll use 0 and 0 as our starting slope and intercept. And then we can calculate the loss, okay? So the loss in vector form is t minus xw transpose times t minus xw. So here I'm doing transpose of t minus xw times t minus xw. Okay, so this is the loss function. This is the loss function of our current points. And so I could say, what is the loss of our w vector right now, which is 0, 0, and it says, this sum of squares residuals. So this is the sum of squares, not the average. The sum of squares residual right now is 446.57. I can say, okay, well, what if we used our already known best answer of 1.83.1, and here it says, okay, the sum of squares residuals there is only 0.06. Okay, so here, we're just dealing with vector form of our loss function. So far, so good? Okay. You know what? We don't need install package numeric derivative. Okay. All right. Here is the function for the gradient of the loss function. Okay. And so we calculated this earlier here as, what do I have? Oh, okay. So here I have x transpose times t, x transpose times t. I guess I factored out the negative here. Okay, so I have negative x transpose t, and then that would be a plus x transpose x w, okay? X transpose x w. So this is our loss function. I've just distributed the negative sign, okay? And 2 over n is just a constant, so I've kind of thrown it out. I could include it, but I've thrown it out, and I'm gonna just take care of this constant factor by using a, by including it in kind of our lambda function, if that's okay. So effectively, I'm just looking at this part right here, x negative, I'm distributing the negative, so I got negative x transpose t plus x transpose x w, okay, and so that's what we have. The gradient of our loss function at whatever our w vector is going to be x transpose t plus x transpose x w. Is that okay with everybody? All right, and so we can kind of test our gradient loss function here. So let's say my w vector is 0, 0. I can say, what is the gradient of the vector 0, 0? Okay, and it says, you know, here our gradient is negative 33 for the intercept and negative 124.7 for the slope. Okay, if I plug in the values 1.8 and 3.1, which we know to be the optimal solution, what should the gradient be at the optimal solution? 0. The gradient should be 0. It should say, I have nowhere to send you. There's no steepest descent anymore. The gradient at that point, once we find our optimal solution, is 0. And when we do that, that's indeed what we get. We get 0 and, you know, 10 to the negative 15. Okay. So because of, you know, calculating and rounding errors and things like that, we get something like that. And if so, you know, if I plug in a number that's too big, 2.8 and 4.1. This tells me, you know, we're starting to veer off in the other direction, and so it gives me a positive gradient over there, okay? Or if one of these is too small, okay, it points me in the direction that of steepest descent. So we want to go in the steepest descent, and so we're going to go in the opposite direction of what the gradient says. Is that okay? All right, so here, I'm going to just start with some arbitrary point 0, w vector 0, and I'm going to use lambda equal to 0.02. This is just a value for lambda to make sure our step is small. Now remember, I've kind of included this negative 2 over n. I've taken it out of our gradient loss thing, so it gets kind of thrown in here for our lambda. And so all I'm doing is I'm just taking my w vector, and then I'm subtracting off lambda times the gradient of our w vector, right? So our gradient function returns, you know, a two-dimensional thing. So all I'm doing is I'm subtracting this off from there, okay? And so I'm just starting off at 0, 0. So if I start off at 0, 0, lambda 0.02, and I'm just going to run this loop, okay? You just say, take 1,000 steps here. And I can ask, you know, what is the resulting w vector? And we're pretty close to where our optimum is. It's pretty close to 1.8 and 3.1. We're just off by a tiny factor here. Okay, and so this is the gradient descent working right here. We're taking tiny little steps in the direction opposite of what our gradient says is the steepest descent, and that's going to take us to the minimum. Let me just kind of illustrate what this does visually, okay? And so in order to, I had to write a bunch of functions just to create a plot here, okay? But in essence, this is the gradient descent vector, gradient descent algorithm. The next value that we're going to use is our current value minus lambda times our gradient at that point, okay? So here I have to create a bunch of stuff. So I have to create like a points matrix and create a way to calculate our loss function at all of these things, just to get this stupid thing, not stupid thing, but create a contour plot, okay? So let me just show you. This is our contour plot. One of the options that I'm using for the contour plot is aspect ASP equals 1. This preserves an aspect ratio of 1, okay? And that's important if you want to see that indeed the gradient is perpendicular to the contour lines, okay? So anyway, all of that code just produces, this is the contour plot, and we can see that this is going to be the spot that minimizes our loss function. So this is the contour plot of our loss function. Our loss function is the, sum of squared residuals, or the average squared residual, and we can see that the minimum happens at 1.8, 3.1. It's going to happen right there. This is the minimum. Over, using different values of the intercept and different values of the slope. Okay, and so this is where we want to go. And so here I can illustrate, wherever I start, okay, I'll start here at, so this is all code to illustrate, where I started. So I'm going to start off at -1, 2. I'm going to start at this point, and we're going to take a whole bunch of little steps, okay? And I'm going to plot those steps, and here's my picture. Where'd it go? Okay, and so, we start here and we're just moving perpendicular. The steps are tiny little steps. We keep going down. This is the direction of steepest slope, and we can see, once we get here, it starts to take a little turn, and then this is now the direction of steepest slope. So all of these are perpendicular to our contour lines right there. Okay. And I can start at another point. I could start, over here, and we would see something similar. So if I start here, where's it perpendicular? So that looks like what, 4.2. We can start there, start at 4 and 4.2 as our starting spot. We'll run the gradient descent algorithm and plot those points. Okay, well, I didn't delete the other one, but so we're starting here. This is the direction of steepest descent. Once we get to here, the direction changes and we move along this way here. Okay, so there we have it. Let me recreate our contour plot. Okay, one of the things about gradient descent is that we're using this lambda that says we want to make sure we're taking small steps. Okay, and so I wanted to show you what happens if we use a step size that's a little too big. Okay, so here my lambda is 0.05. I'm going to start off at -1, 2, and we're going to run this. We create our new contour plot, and I'll run these points here. Here, let me just do red. Okay, so here is my first one, and I'm going perpendicular, and the step size shot me all the way out over here. Okay, I used a step size that was too big, so it shoots me out over here, and it hits this contour plot. Luckily for us, this contour plot still says, okay, we're going to go back over here, and you can see it bounces me over here, and then it just keeps bouncing back and forth. And so if we were to look, this line is going to be perpendicular to the contour plot right here, and we trace it over here. It hits this contour line. This line that shoots off from there is perpendicular to the contour plot at that point, and so on and so forth. It still manages to get us to the minimum. Okay, but other times you start off somewhere and you take a step size too big, and it takes you in the wrong direction. So maybe if I start close, let's say 1.5 and 2.7, but let me just kind of crank my lambda up to be a little bit too big. Okay, yeah, well, I did it too big. So we started off over here, and it just diverged. Okay, because the step size was too big, it's diverging, and it's sending me in the opposite, sending too far away. And maybe 0.1 was too much. Let me just try 0.07. Let's see. Yeah, it's still diverging, but it's going all over the place. Okay. Again, you know, let me just shrink back my lambda, we can see, you know, I'm starting here and it should just go down to here. Okay, that's what we want. Okay, but you know, I've taken step sizes that were too large, so I've, you know, basically this is shooting me over here, and at that point, the gradient is even bigger than my starting gradient, right? So the gradient is even bigger, and so it just shoots me in the opposite direction. I can probably try to fine tune this. It's probably at like 0.058 or something. Just playing around with it. Okay. And so maybe, let's just do like 10 steps. Sorry. So you can kind of see where it's starting to go bad. So we start here, it shoots me over there, and the gradient just keeps getting bigger and bigger and bigger because my step size is a little too big, and so it just diverges. So that's one of the things. You got to make sure you're using a lambda that's too small. But on the other hand, if you use a lambda that's too small, then your step size is going to be, you're going to just walk down the thing too slowly. You're taking too small of a step that you're just inching along towards the solution. So that's you know, there's a little bit of a trade-off, and as far as what step size you need to select for gradient descent. But the idea behind gradient descent is simple. You just find the gradient, take a step in the opposite direction, because the gradient points in the direction of the steepest ascent. Yeah.
Would it be possible to have like lambda change so that it like kind of passes out of the approaches, and then you don't have to worry about?
Yeah, if you look up the Wikipedia article on gradient descent, they talk about selecting your lambda, and you can have lambda itself be a function of the values you're using, or the last series of values that you're using. That's certainly probably recommended. But as far as for our first illustration of gradient descent, I just used a constant for the lambda. But yes, we can certainly make our algorithm a little bit more complicated by having lambda adjust as the algorithm progresses. Okay.
What does the lambda adjust upon? What is the function of for that?
So the lambda, so the gradient at any point tells you the direction of the slope of steepest descent. Okay. Now it gives you back a vector. Okay, a vector that says this is the direction, and it's not like normalized or anything, and so that vector could be quite huge. And basically, lambda just adjusts it so you're not you're just, instead of taking adding that vector directly to your current location, you're just shrinking that vector down to something small, so you're taking a small step. Okay, so it could be, you know, how do I get to I don't know, wherever, you know, how do I get to another location on campus? And you can say, oh, you need to travel east, okay? But when we give you directions in vectors, we don't just say just go east. It's always a direction and a magnitude, right? And based on the way we calculate our vector, that magnitude might, or oftentimes is quite large. And so instead of just saying, you know, taking a step 1,000 miles east, we might say, oh, just go 100 feet east or something.
Okay. My question was, you said there are functions that can vary from like the size of lambda as you kind of goes along. What are those functions?
So functions that adjust lambda will make lambda often a function of kind of your maybe the last step size, or the amount of change between you know, your previous steps and things of that nature. Kind of looking at how big of a step you took in the past and using that as a guide for how big your future steps should be. If you're interested, we can keep talking about that in the future. Let me just kind of show you how we can implement gradient descent using the partial derivatives, okay? And you can always look up gradient descent on Wikipedia or just Google, and you'll find a whole bunch of stuff talking about it. Okay, this is just under a classification of what we call numeric methods to minimize a function, okay? And so, you know, I mean, we looked at a few numeric methods in 102A. Here we've got another way. Okay, so this is gradient descent. So I showed you gradient descent where we were using vector notation. We can do gradient descent using non-vector notation. Okay, because the gradient and defining the gradient as the partial derivatives, which is the definition of the gradient. Okay, so we said, you know, the gradient of some function we can say is the partial derivatives of that function. So we could say the gradient of L with respect to W is going to be the gradient of our loss function, the partial with respect to W0, there's no vector there, just W0, and the gradient of the loss function with respect to W1. Okay, and we can transpose that. And so if we calculate the partial derivative of the loss function with respect to W0, okay, this is going to be with respect to W0, and now because I'm in non-vector notation, I'm going to have the sum from n equals 1 to n of t sub n minus so that's what we have there. Okay, and so when I take the partial with respect to W0, this is really just an application of the chain rule. So, and the derivative of a sum is the sum of the derivatives. So I'm going to just take this out, and applying the chain rule, I have 2 times 2n minus W0 plus W1xn. And then I'm going to multiply this by -1, chain rule, right? And so this gives me -2 over n Let me just distribute the negative there. All right, so this is the partial with respect to W0. We can do the same thing with respect to W1. So this is going to give me multiply this by negative W, no, sorry, not negative W1, negative x of n, okay? And so when I pull this out, I'll get -2 over n equals 1 to n of x of n, t over n minus W0 minus W1 x of n. Okay, so these are my partial derivatives, and so if I want to implement this, and we say the next Wn plus 1 is going to be our current Wn minus lambda times our gradient of f, this effectively says that our next Wn, which is going to be the vector W0 at time n plus 1 and W1 at time n plus 1 is going to equal, and now I just have to, I'm going to split this. It's going to be our current W0 at time n minus lambda times this whole business here. Okay, so I'm going to just say the partial of L with respect to W0. So that's all of this, and then the next point will be W1n minus lambda with the partial with respect to W1. Okay, and so this, it's the exact same thing as we had earlier, but here it's expressed as partial derivatives rather than the gradient in vector notation. So on the previous slide we had the gradient in vector notation, and here we have the gradient but expressed as a kind of the combination of its partial derivatives, as a vector of its partial derivatives. All right, is that good with everybody? Okay, and so I can implement this in R as well. And we have the code gradient descent for linear regression using partials. What's going on with my... Okay, and so the code here, it's the same. We've got the error, x vector, t vector, points, column names. I've got the loss function. Okay, and this is how we're going to calculate the gradient with respect to W0, okay? And so here, just taking a quick look at what this is, it's taking the sum of each value, each point t, minus this, and it's calculating all of this. So this is the gradient, or this is our partial with respect to W0, okay? And here I've gotten rid of the n, but here I got, you know, -2 times, and it's taking our point t minus W0 minus W1 time x, okay, which is what we've got right here, right? T minus W0 minus W1 x. And it's a sum, so we're going to add that to the current value of the gradient, and it returns the gradient. We do the same thing for the gradient or the partial with respect to W1, okay? And that is x of n times Tn minus W0 minus W1 xn, and we can see that's going to give us the point x times t minus W0 minus W1 times x as well, okay, as we work through all of the points in our data. So that's what we have there. So this gives us how to calculate our W0 and our W1. We again set up a way to plot our contours just as before, and here I can start with, oh, I called it alpha here. Let me just, well, I apologize. Some textbooks use alpha, and earlier in my other slides I used lambda, but it's the same concept. So lambda and alpha, depending on who you're reading, it's the same thing, okay? I apologize for the notation switch, okay? So basically we have all of these things, okay? I'm just setting up places to store all of our results. And so we're going to take a step in the W0 direction, okay? And then we would just take, that's going to be alpha or lambda times our gradient with respect to our partial with respect to W0, and a partial with respect to W1. And then so our next value of W0 is going to be W0 minus the step in the W0 direction, and the next W1 is W1 minus the step in the W1 direction. So we do that. We update that, and if here I'm just keeping track of our step size, okay? So we do that, and these are the values that we ended up getting. Okay, and so here after 150 steps got me to right here. I probably need more than 150, maybe 200, maybe 500 steps or something. And so this is gradient descent as applied to linear regression, okay? Trying to minimize our loss function for linear regression, which is the sum of squared residuals, okay? All right, and when we come back to class, we'll use gradient descent for, I think, a really cool application. So we'll take a look at that. Okay, we'll see you guys in a couple.